In today's lecture, we will be starting a new topic. In today's lecture, we will be covering the work and the kinetic energy and the work energy theorem. So at the beginning, we will be looking at the work that is due to a constant force, and then we will introduce the kinetic energy and the work energy theorem. So what is the work? What does work mean here? Work is an energy that is transformed to or from an object through applying a constant force. In this case, we will be looking at constant force that resulted into a displacement. So that force, if it's applied on an object, the object is going to move. This force, as we have seen before, will result into an acceleration, and this acceleration is going to change the velocity of that object. If this acceleration is in the same direction of the motion, it will increase this velocity, or if it's in the opposite direction, it will result into slowing down that object. So what is the expression for the work? The work is found by this expression. W equals to the product of the magnitude of the force that is exerted on the object and the magnitude of the displacement times the cosine, the angle between the vector of the displacement and the vector of the force. So if you look here at this man who is pushing this lawnmower, he is exerting a force on that lawnmower. This force resulted into the lawnmower moving a displacement. So my displacement as a vector between this point and that point as delta R vector. And the force is applied, as you can see, along the handle of the lawnmower. So if we want to calculate the work, you take the magnitude of the force times the magnitude of the displacement times cosine the angle between the displacement and the vector, which is theta here. Now, notice that this expression is a function of theta, which means as long as theta is not 90 degrees, you have a work. If theta is 90 degrees, then the work exerted due to this force that is perpendicular on the displacement is 0, because it's a function of cosine theta. In other words, if the angle between the force and the displacement is 90 degrees, based on this expression, the work is 0. Now let's look at this example here where we have this couch being pushed up along this inclined plane with a force F. And as you can see, the displacement is along this inclined plane with the displacement delta R. How can we find the work? You can redraw them such that the tails, they start at the same point. And then the angle in between is theta. This is the angle that you take when you calculate cosine theta. So in this case, W would be magnitude of F times the magnitude of delta R times cosine theta. So there's an observation that I want to pay attention to here. In this expression, we took the magnitude of the force, right? And that's why we looked at the theta in between, and we took the cosine theta as well. But what happens if you project this force on the x and on the y, and if you take the x to be along the inclined plane? If I am to rewrite the expression that I just mentioned, which is W equals to F times delta R times cosine theta. Notice that I took the magnitude of F for that force, and I looked at the angle between that force and the displacement, and took this cosine theta in this expression. But now, if I am to decompose this F into the Y component and the X component, and I try to calculate the work due to the Y component and the work due to the X component, what am I going to get? Let's see. If I take the X-axis along this inclined plane, this is delta R, and the Y perpendicular on that surface, then Fx, and then I solved for the work for each of those components. So let me do Wx due to the X component. So now I'm not looking at the total force, I'm looking at the components of this force. So in this case, Wx would be Fx times delta R times cosine. What is the angle between Fx and delta R? 0. Both are overlapping, right, in the same direction. So this is 0. Which is Fx delta R. Now let me calculate Wy. It is Fy times delta R times cosine. Cosine what? What is the angle between Fy and the displacement? $90 degrees, which is 0. So Wy is 0. So the work due to the Y component is 0. Why? Because the Y component is perpendicular on the displacement, and that makes it 0. But let's look at the work due to the X component. Wx is Fx delta R. Is that right? And what's this Fx? It is F cosine theta. So I can say that this is F cosine theta delta R. Isn't this the same as this? They're the same, right? What does this tell you? This tells you that the component that is responsible for the work is the component that is along the displacement. of the force. The component of the force that is responsible for producing the work is the component that is along the displacement, and which is the X component in my case here. Either way are going to give you the correct answer. But the intention here is to show you, to demonstrate to you, what is the meaning of this cosine theta. The meaning of this cosine theta is to find the effective or the component, the value that is responsible for producing that work. Is that clear? Yes? Okay, great. So here, if you have the chance to decide on the coordinates, and you took the coordinates such that the X component is along your motion direction, where this is what we have done. We tilted the coordinates and we took X along the inclined plane. But in case you were not given the choice to do so, and you were given two random vectors, and you want to calculate the work such that the displacement has an X and Y component, and the force also has an X and Y component. What is the general approach to solve or to calculate the work? We're not going to go in details and show you how did we get this expression, because it is simply the dot product of those two vectors that is outside the scope of this lecture. But let me tell you that the work here is the summation of the product of the X component and the Y component. So my force here has X component and Y component. My displacement delta R here has X component and Y component. So if you've been given the work and the force, that both of them, they have an angle between with the coordinates as this way. In this case, you find the components of the force and the components of the displacement, and you take the X component of the force, multiply it with the X component of the displacement, and then you add it to the Y component of the force that is multiplied to the Y component of the displacement. So this is the general approach for calculating the work in two-dimensional problem. Is that clear? Yes? Okay. So let's move on. This work is a scalar quantity. The unit for the work is joules. Again, this is what we have shown as a general approach for calculating the work in a two-dimensional problem, where the coordinates are having an angle with both of those vectors. You're not given the choice to choose the coordinate the way that you wanted, such that it is aligned, for example, with the displacement. No, you're given the coordinate such that it looks general like this. So let's solve this example to understand how do we calculate the work by a force. In this example, you're pushing a 9-kilogram lawnmower with a constant force of 14 Newton across the flat lawn. The lawnmower handle makes an angle of 25 degrees to the vertical, neglect friction. It is extremely important to pay attention to the angle and the reference of the angle. So the angle is between the vertical axis and the force. Now, part A, if you do 27 joules of work on the lawnmower, what is the resulting displacement? So he's giving you the work that you've done on the lawnmower. He wants the displacement. B, what is the work done by the normal force on the lawnmower? So let's start with the free body diagram for the problem. So here we have the lawnmower. And we have the force pointing in this direction. I will call this one FP. And then we have the normal force. And we have the gravitational force. Now the angle between the vertical and the force is 25 degrees. So this one is 25 degrees. I will put my coordinates right here. X and Y. So this 25 degrees is between the vertical and the force, which means my theta between the displacement. Now what's going to happen? This is my lawnmower. This lawnmower is going to move. Right? So from here to there, I'll make it in blue as my displacement. This is delta R. And my angle here is theta between the displacement and between the force. So where is this angle? It is here. This is the angle that I need to use when I calculate the work. So let's put what I have here. I do have the mass as 9 kilograms. I do have Fp, this is the magnitude as 14 Newton. I have theta as 90 degrees minus 25, which is theta is 65 degrees. It's the complement, right, of 25. What else? I have the work as 27 joules. I need the displacement. So I'll put the expression, which is W for the force. W is Fp, the magnitude of the total force, times delta R times cosine theta. So substituting here, I have 27 equals to 14 times delta R times cosine 65 degrees, and delta R is 27 divided by 14 times cosine 65 degrees, and delta R is 4.6 meters. This is the displacement. This is the magnitude of the displacement. right? And keep in mind that displacement as a vector is pointing in the east direction, right? That's as a vector. So that's part A. What about part B? In part B, we need to calculate the work done by the normal force on the lawnmower. The normal force. Can somebody tell me what is the work done by the normal force on the lawnmower? How much is the angle between the displacement and the normal force? 90 degrees, right? This is the displacement along the x-axis, which is, that's my horizontal surface. And I have my normal force perpendicular on that normal surface, making a 90 degrees to that normal surface, which means here, my theta for this case, when I say cosine theta, it's the angle between the force and the displacement. So the theta for the FP was 65. The theta for the normal force is 90 degrees, which means the work is 0 because the force is perpendicular on the displacement. Is that clear? Any question about how did we calculate the work for that force and for the normal force? Now let me ask you this. If you have a mug weighs 0.5 kilogram, that's sliding along a flat horizontal surface for a distance of 1 meter, slowing down due to friction. So basically what's happening, you kind of gave that mug a push, and this mug went with an initial velocity, but since that table has a friction, that mug went 1 meter, but he was slowing down. What is the work done by the gravity on that mug? When I say gravity, I mean the gravitational force. How much do you think the work was done by the gravitational force on that mug that was sliding on that horizontal table? Zero. Why zero? Because it is perpendicular on the displacement. So the answer to this is 0. You're absolutely correct. Now, this is for the gravitational force. Now, what about the friction? Same mug, same problem. Remember, the table had a rough surface and there was a friction, and that mug was slowing down due to the friction as it slides. What is the work done by the friction on the mug? Can you tell me? Maybe this is not a question that you can answer right on the spot. It requires you to do some calculations, and while you're doing the calculations, you would find out that the coefficient of the kinetic friction is missing. And that's why there's not enough information to decide. But let me ask you this question. Now make it easier here. That mug is sliding and slowing down, right? And there's a friction. Are you expecting the work done by the friction on this mug to be negative or positive? Negative. Why negative? Because the friction is in the opposite direction of the motion of the displacement, which makes the angle theta to be okay. which makes the angle between the friction and the displacement to be 180 degrees. And cosine 180 degrees is -1. Okay, so we're going to come to an example. In this example, we will see how to calculate the friction, the work due to a friction. Okay, so the question reads the following. Your bicycle is slowing down on a flat stretch of road due to a constant frictional force of 43 newtons. So there is a frictional force of 43 newtons. And we have learned that this frictional force is always in the opposite direction of the motion, right? Trying to slow it down. If your total displacement is 210 meters west before coming to a stop, what is the work done by friction on your bike over this distance? You're not pedaling, the bike is just coasting to a stop, which means you're not putting force there. Only the force of the friction is applied on that bike that had an initial velocity, and the friction is slowing it down. So, do you know how to calculate the work here? The first thing to do is start with the free body diagram. This is the first thing to do. And then put all the information that you have. Things will become easier. So here I have the floor, the bike. This bike has normal force, gravitational force. What else? I have a friction in the opposite direction, Fk. And then this is the displacement, where here the final velocity would be 0. Okay? So if I put my coordinates now on here, I need to calculate the work due to the friction. What is the work due to the friction? Before I start solving, let me put, I have Fk as 43 Newton. I have delta R as 210 meter, right? Going west. What is the work? The work is due to the frictional force. I have the work as Fk times delta R times, what is the angle? Can somebody tell me what is the angle between the frictional force and the displacement? -180 degrees, look. Minus 43 times 210, and the work is minus 9.010 to the power minus 3 joules. Any questions so far? Questions? No questions? Okay. So far, we have seen that a force applied on an object resulted into a work exerted on that object. Either this work is positive if that force goes in the same direction of the displacement, or negative, as we have seen in the what the frictional force have exerted on the work as a negative work on that object. So that force resulted into inducing an acceleration, and this acceleration, as we have said, changed the velocity of the object, either increasing the velocity or decreasing the velocity based on the direction of the acceleration with respect to the direction of the velocity. If you know that the kinetic energy is given by half mv squared, and you know that this force that resulted in an acceleration changed the velocity, this means that this force that you have applied resulted into a change in the kinetic energy, right? Because the kinetic energy is a function of the mass and the speed. So if the mass is constant and the speed changes, then definitely the kinetic energy is going to change. Which means that any work that you apply, you exert on this object, is going to result into a change in its kinetic energy. And this is in what I want to say here, that any net work exerted on an object is going to result into a change in the kinetic energy of that object. Which means now I can say that this net work is indeed equal to the difference in the kinetic energy between the final and the initial. All this because of the force, all this because of the acceleration that resulted into a change in the velocity of the object. So at the end, that work exerted on that object resulted into a change in its kinetic energy, and this is what we call the work energy theorem, where the work done on an object equals to a change in its kinetic energy. So that work, the total work, is the kinetic energy at the final destination minus the kinetic energy at the initial destination. So that's why we say W total equals to half mv squared, where v here is the final, minus half m v naught squared, where v naught here is the initial. So we're talking from the beginning of the work till the end of the work. The change in the kinetic energy is related to that work. And this agrees with what we have seen in Newton's second law. When we had a force resulted in an acceleration, this changed the velocity of the object. So this is what we call the work energy theorem. Work done on an object equals to the change in its kinetic energy, such that the final kinetic energy minus the initial energy, kinetic energy equals to that work. So the unit for the kinetic energy is joules as well. And as I said, work total equals to EKF, which is the final, minus EKI. And this is delta EK. So whenever you see delta, this delta means final minus initial. Delta here is final minus initial. That's why we say delta EK, which is delta EKF minus, which is EKF minus EK initial. Any questions so far? Any question about the work energy theorem? So let's do this example. This is our last example for today. In this example, we have the following. We have an ice skater of mass 55.2 kilogram falls and slides along the ice, undergoing a horizontal displacement of magnitude 4.18 meter before stopping. Pay attention to the word stopping and how does that word is being interpreted. The coefficient of kinetic friction is 0.27. So we have an ice skater that has pulled and slid along the ice. The only force he is having is the frictional force. We've been given the coefficient of kinetic friction as 0.27. We've been given the displacement he went, 4.18. We want to calculate the work done by friction as the skater slides. So again, the first thing to do is to draw the free body diagram and pay attention to the displacement vector. It is extremely important when you calculate the work to identify your displacement direction. So I have the ice skater here. Here, where he started to slide. So he slid all the way to here before he reached the final destination. So my displacement here is delta R. I have V naught, the initial, that I don't know. I don't know the initial velocity. But what I do know is the final velocity, which is 0, because he stopped. This is very important. That's why I said pay attention to the wording of the problem. He stopped, meaning that his speed is 0 right at the final destination. Normal force, gravitational force, frictional force, Fk. Now, let me put my coordinates. I need the work done by the friction on the ice skater. W. Before doing this, let me put what I know. I have mass 55.2 kilograms. I have delta R as 4.18 meter. I have a mu K as 0.27. Now I need the work. The work of the kinetic frictional force. W equals to Fk times delta R times cosine theta. How much is theta? 180 degrees. Look at the angle between the displacement and the frictional force, 180 degrees. So I have theta as 180 degrees. What is the frictional force? Do you know how can I calculate the frictional force? Yes, go ahead. Exactly. So Fk is mu k times the normal force. How can I calculate the normal force? Yes. Apply Newton's first law along the y-axis, which is sigma Fy equals to 0, and this is going to end up with Fn positive minus Fg equals to 0, and Fn equals to the gravitational force. Or Fn equals to m times g, or Fn is 55.2 times 9.8, and Fn is 541 Newton. So if this is Fn, then Fk is 0.27 times 541, and Fk as 146 Newton. Again, as a magnitude, right? Now I can substitute into the work. So I have 146 times 4.18 times minus 1. And the work is W is minus 610 joules. Right? That's the work. Negative work expected because the kinetic frictional force is in the opposite direction of the displacement. Now, what is part B? Part B is, what is the skater's initial kinetic energy? What is the skater's initial kinetic energy? So if I come here and I put work equals to delta EK, right? And this delta EK indeed is EKF minus EKI. I need this initial. I need EKI. What do I know about the final kinetic energy? It is 0. Why 0? Because it stopped. If I go here and put the equation and substitute the kinetic energy final, it is half mv squared minus EKI. Remember, what did we say about the final velocity? Because it stopped. The speed was 0, right? So this one is 0, which means that W equals to minus EKI, or EKI is minus W, or EKI is 610 joules. See? What is the skater's initial speed? Fine. We found the initial kinetic energy. Now we want the speed. Do you know how we can calculate the initial speed? Yes, we had here EKI equals to half m V naught squared. Rearranging, I have V naught squared equals to 2 times EKI divided by m, or V naught as square root of 2 times EKI divided by m, 2 times 610 divided by 55.2, and V naught is 4.7 meter per second. So this is how we calculate the work, the kinetic energy, and also the speed, knowing the kinetic energy. So this ends our lecture for today.